Hi everyone, today I'm your teacher, Kok Simai. I'm from the SMK Tinggi St. David. Today I want to teach about the lesson that's a chapter 4, 4.3, specific latent heat. Let's see the notes. Okay, let's see first one we want to introduce is the latent heat. What means of the latent heat? Latent heat is absorbed and also the heat released at the constant temperature during changes of the phase. So latent heat, the meaning is there never changes about the temperature, but the situation is changes the phase, using the heat to absorb and also using the heat to release. Okay, now we're going to see got four of the main phrases here. The first one is a melting, then followed by the solidification, boiling, and also condensation. Let's see the diagram here. The first one, there's a melting. Okay, melting is a situation when the solid, they become the liquid. For this one situation, the latent heat will be absorbed. Another situation, the latent heat also absorbed, there's a boiling. Okay, boiling is from the liquid, they become the gas. Now we go to reverse back. From the gas, chain become the liquid, we call it condensation. This situation, you find it, the latent heat will be released. Okay, another situation, we continue liquid, go to the solid. So this one situation, we call it solidification. Latent heat also release. So one more is an extra. There's a from the solid, straightforward become the gas. This one, the process, we call it sublimation. Latent heat also is absorbed. Now we go to the next one. They introduce specific latent heat. Specific latent heat means total amount of the heat they require to change 1 kg of the object without change in the temperature. So this one is a definition related with the energy and also the mass of the object, but not related with the temperature. Now we can see about the formula. Q equal ml. Q is a heat absorbed. You also can say there's a heat released. Okay, mass is a mass of the material. Then the L is a specific latent heat. So this one is what I want to introduce today. Okay, L stands for latent heat. Now if you want to find the L, then the mass should be moved to another side. Q over M equal to the L. So from here, the unit for the latent heat should be joule per kilograms. Okay, now we're going to see the situation related with the latent heat. Okay, first one is a solid become the liquid. Just now I show you that one is a melting. So this one situation, they'll be using the specific latent heat of fusion. Another one is liquid, go to gas, that's a boiling. They'll be using the specific latent heat of vaporization. The symbol for the fusion, there's a LF. Another one is vaporization, there's a LV. Now we're going to see the introduction. Okay, introduction for the specific latent heat and also fusion and vaporization. Okay, definition for the latent heat fusion. The first one is amount of heat that required to change 1 kg of the substance from solid to liquid phase without change in the temperature. For the vaporization, almost the same definition. We just want to changes about the phase name. Okay, now the amount of the heat required to change 1 kilogram of the substance now is from the liquid become the gaseous, okay, without change in the temperature. So this one is a definition for fusion and also vaporization. Okay, now we're going to see the heating curve. Okay, let's see the heating curve. Okay, we separate by 2 points. One we call it melting point, another one is a boiling point. Okay, let's see the A to B. A to B, you can see the graph should be go up. Okay, C to D also is up. D and E and F also is up. So from this one situation, you find it the temperature keep increasing. When the temperature keep increasing means this situation not related with the latent heat. Because just now we find it latent heat is not related with the temperature. So from here, we're going to see the state of the metal. Okay, A to B, the metal should be solid. Okay, then when they achieve to the B, solid, they start to melt. Okay, B to C, can you see there's a flat constant? The temperature become constant. Temperature become constant means that's a latent heat occur. So B to C, the situation is a solid and liquid, means this situation they start to split out. That means the molecule, they start to split. Then from the solid, they want to become the liquid. Okay, until achieved to the point C. So you find it melting complete. The whole object already melting complete, become the liquid. Okay, after C, the temperature continuous increasing. So from C to D, actually we don't have any changes the phase. They just increase the temperature, means kinetic energy increasing. So C to D, the matter should be liquid. Okay, until D, now the liquid, they start to boil. When they start to boil, that means they want to change another phase. So D to E, this situation, constant again the temperature. So latent heat of vaporization will take place. So from D to E, the matter should be liquid and also the gas. So that means now the liquid, they want to split again the molecule, okay, become randomly moving molecule. So there's a gas. So until E, boiling point already finished. There's a last part for the boiling point. So E to F, the temperature continue to increase. Now this situation, the matter is all become gas already. Okay, now we go to one point to explain the situation. T1 is stand for melting point, then T2 is a boiling point. Okay, now we're going to see the QR and ST. Q and R, S and T, this one is a flat point. That means the temperature become constant. Then the question will ask why the temperature constant, although the heat still provided. So your answer should be because the heat supply they use for the object to use overcome the forces. You must say overcome the forces of attraction that hold the particle together. Then after that, heat absorb. Heat absorb, there's a QR and ST. We call it as a latent heat absorb, but we got separate. QR we call fusion. ST we call it as a vaporization. Now we go to cooling curve. Cooling curve, the graph is go downwards. Can you see the graph should be decreases. Okay, when it decreases, we go and see one part by one part. PQ. PQ, they start with the gas. Until to the Q, Q we call it as a condensation point. Condensation point means now the gas, they start to condense. They want to change the phase. When they change the phase, this one situation should be constant temperature. So what should be take place? The latent heat will take place. This one is a latent heat of vaporization, but now is release. You want to release the heat. So until R, condensation already complete. Condensation when just complete, now the temperature will keep dropping. When keep dropping, this situation RS, we find it as a liquid only. Okay, they keep dropping, that means they never changes about the phase. They just change about the temperature. So RS, the situation is a liquid matter. Until S, liquid, they want start to freeze. So S to T, that's a constant temperature. They want to start to change about the solid. So as the T, S to T, the situation should be liquid and solid. Okay, so from here, S to T, what should be taken? There's a latent heat of fusion that will take place here. Until the freezing just complete to T, now the temperature will continue to drop. So when they continue to drop, that means they just got one of the phase at this one situation, there's a solid. Okay, from the T to U, after that U to V become constant again. This one is a temperature stay at the room temperature. Okay, so this one is a meaning from this one cooling curve. Okay, now we're going to see the explaining for the point. T1 we stand for condensation point. T2 we stand for freezing point. And the T3 is a room temperature. During the QR, okay, we're going to see the QR is a flat one. ST also is a flat one. These two lines should be unchanged temperature. Okay, why the temperature unchanged? Although you keep releasing, you go to release the heat, but the temperature still constant. Okay, reason is because the heat energy released to the surrounding during the formation. Okay, they want to formation the bond. Just now heating is you want to break the formation of the bond. Now you want to join back. So they say formation of the bond. So the heat energy that release QR, we call it as a latent heat of vaporization, but that's a releasing. S to T, Also, it's a releasing, but this one, the name should be the same, latent heat of fusion also. So this one is why the temperature keep constant, although the heat provided, because they want to release the heat to join back the bone. So that's why the temperature keep constant. For this one situation, they're just using the heat to join back the bone, then become the chain and other phrase. Okay, for this one topic, we got two of the experiment. Okay, first one, there's a specific heat, latent heat of fusion. They want to find it, what is the number. Another one is a latent heat of weabilization for the water. So let's see what apparatus they're using. They're using the heater, filter funnel, beaker, electronic balance, power supply, stopwatch, and rheostat. Okay, now we see the procedure. Okay, first one, the beaker for the experiment set. Okay, we got two sets. This one is the experiment set, another one we call it control set. They put on the electronic balance respectively. Now they need to reset the reading of the both electronic balance. Make sure they start from the 0. Now the setup apparatus that's shown in the diagram. Okay, when starting, both beaker and also electronic balance are not below their respective filter funnel. Okay, now we're going to see the diagram here. Okay, we got two beaker and also the electronic balance. Okay, one is a control set, another one is an experiment set. Okay, what means of control set, what means of experiment set? Okay, control set means they never join with the power supply. Experiment set, that means they will join with power supply. But control set, you find it, the ice still can be melted. But you join with the power supply, sure you find it, the mass of the ice to melt must be more than the control set. Reason is, control set, the ice melt due to the heat from the surrounding. For the experiment set, the heat melting because of two. There's a surrounding heat and also from the heater. Okay, now they switch on the immersion heater. For the experiment set only, when the water is dripping out from the filter funnel of the mixed rate, so you set the time. Okay, now place the beaker and the electronic balance respectively below the filter funnel. Start the stopwatch. After for 10 minutes. So they record the reading from the mass of the water collected in the beaker, experiment set, and also the control set. So experiment set we label there's a M1, control set there's a M2. So now you switch off all the immersion heater and record what is the power of the immersion heater. Now we need to fill in the result. For M1 and M2 you need to set up, you need to write out. For the M1, that's the experiment set. Sure, the number of the mass is bigger than the control set. Then the power you can record from the power heater. Then the time taken you set by yourself, but using the second. For this one experiment, we assume no heat loss to the surrounding. Means all the electrical energy just supplied, they will all absorbed by the melting ice. Now we're going to see specific latent heat, how to count it. Okay, we're using the formula PT equal ml. So from here, we're never using the Q because you supply by power supply and also time taken. So you want to find the latent heat, we're using PT over M1 minus M2. Means the mass of the experiment set minus the control set. Okay, we do want using the control set. Because control set is surrounding to make it melt. So we need to minus. We just want the mass of the ice melt by the heater. So we need to minus. Okay, finally the conclusion we find it, specific latent heat of fusion of the ice is one of the constant number. Okay, we just compare with the standard. So this one is what we need to find from this experiment. Okay, second one also the same thing. Now they want to find is the latent heat of weabilization of the water. So from here they're using a high power immersion heater. There's a 500 watt power supply, beaker, electronic balance, and also the stopwatch. Okay, then the material they're using is water and tissue paper. Tissue paper, the function should be they want to prevent the heat loss to the surrounding when they start to heat the water. Okay, now they set up shown in the figure. Switch on the immersion heater and wait until the water boils because now we want to boil the water. So you must make until the water start to boil. Okay, when they just start to boil, you need to start your stopwatch. At the same time, record the reading from the electronic balance. That's a M1. Okay, after 5 minutes, so this one is the time taken, you record the reading of the electronic balance M2. So the M2 sure less than M1 because you start boiling means some of the liquid already become the gas. They will boil, they become the gas already. So from here we find it, the reading for M2 must less than the M1. Now after that you need to switch off the immersion heater, then you record what is the power. Now we're going to see the result. The result also the same. You got separated by M1 and M2. You must using the M1 minus M2. Then the next one is the time taken, depend for your. Just now we're using 5 minutes, then 5 minutes. Then the power, then you can record it from the heater. Then the assumption also the same. We say no heat loss to the surrounding. Then the electrical energy just provide the energy or will absorbed by the vaporized water. Specific latent heat of vaporization can measure by using this formula again. PT over M1 minus M2. Conclusion, latent heat of vaporization of the water is a one constant number. So you need to compare with the actual reading of the vaporization of water. Okay, this one is a 2 of the experiment. Just want to measure what is the reading of the latent heat of water and also the ice. Okay, now we're going to see the changes of the phase of water. Okay, first one, let's start with the ice. When the ice just melt, the ice molecule, they will absorb the latent heat of fusion. After that, causing the ice to change from the solid, become the liquid. So another situation is start to boil. When the water, they start to boil, the molecule, the water molecule, they will absorb the latent heat of the vaporization. After that, causing the water to change from the liquid, become the gas. Okay, now we're going to see the third method is when the water vapor, they condenses. Okay, now they reverse, they want to condenses. The water vapor molecule release the latent heat of vaporization. Now this one situation, they want to release the heat. So after that, causing the water vapor, they change back, become to the liquid. Okay, from the gas, go back, become the liquid. Okay, now we see some application. Okay, first one is a cooling drinks. So in the ice box, you put full with the ice and also the drinks. After that, you find it when the ice just melt already, but the temperature of the drink still keep in cool situation. Why? Because when the ice just melt, the latent heat surrounding, the latent heat of fusion, they will absorb from the drinks. So that means surrounding the temperature become low because they already absorbed by the latent heat to melt the ice. Now we go to the sweating. Sweating is a situation when your sweat on the surface of your skin that evaporate. When they evaporate means they from the liquid, they become the gas. When the liquid become the gas, the situation is a changes the phase. So this one changes the phase means latent heat of vaporization absorb. Absorb from where? Absorb from your body. Finally, you find it your body will cool down. The heat already released. Okay, the third one is a steamer. The steamer go to steam the food. Okay, how they go to steam the food? So inside must have the water. Okay, water, large amount of the water, when they just heat, when they become boil, then after that, the condensation back become the gas because the whole system is enclosed. When the condensation back become the gas, that means now the situation is latent heat of vaporization release. When they release the heat, where they go? They go to the food. So finally, your food in the steamer faster to heat up. Okay, then we're going to see some cooling system in the refrigerator. Okay, the refrigerator, they're using the cooling effect from the evaporation. During the circulation of the cooling agent, heat is absorbed from the inside the refrigerator. After that, they're released outside. Okay, now we see the step. First step is from the compressor. Let's see the compressor. Compressor is a cooling agent gas. Okay, when starting is a gas, to increase the pressure and its temperature. Okay, after that, when it go up until second part, there's a condenser. Heat is released. Okay, heat is released from the refrigerator. This part is a condenser. Condenser means from the liquid, from the gas. Okay, they will condense back, become the liquid. So from here you see in the condenser, cooling agent, there's a gas, releases the latent heat during the condensation. Okay, so the heat will be released from here, then after that they will become the liquid. Okay, now when they go to part 3, the expansion valve. Cooling agent now become the liquid already. They flow through the expansion valve. Go where? Go to the freezer. Now you're going to see the freezer part, there's a number 4, heat is absorbed. All the heat from the refrigerator means your food you put in, you got heat, is it? They will absorb until to this part. Until to this part, they will evaporator. So evaporator means in the evaporator, the cooling agent, that's a liquid. They will evaporate and also absorb latent heat from inside the refrigerator. All the heat in the refrigerator, they will absorb it. So you find it, refrigerator now is cool because already absorbed. So when the liquid just absorbed the heat, after that they will become the gas again. So from here, they go to part number 5, they will come down. Cooling agent become the gas, flow up from the evaporator to the compressor. So after that, cooling agent is a liquid, they absorb the heat from the refrigerator, they will come out back as a cooling agent, that's a gas. Then they flow back to the evaporator to the compressor. So this one process should be repeated. So in the freeze, normally it's a cool because the heat already absorbed. So behind the refrigerator, you find it there's a hot gas because the heat is released. Okay, now you can see some example question. Okay, first one, the question, let's see. They give you the heater, 480 watt, immerse into the one of the beaker. They want to melt the ice. Okay, now you find it, they're using how long? 120 seconds. The reading of the electronic balance decreases by 0.172. That means when starting, maybe it's higher lah. After the heat, they become 0.172 kilograms. Now they ask what is the mass of the ice that has melted during the heating period. So from this one situation, what we assume? Okay, we assume ice is melted by the heat from the immersion heater only. Okay, we never talk about the surrounding because we assume no heat loss. All the water from the melting ice flow out of the container. So that means after they just melt, all the water will flow up to the sink. So that means now the electronic balance, they measure just the balance of the ice got how many. Okay, now related the change in the reading of the electronic balance to the mass of the ice which has melted. So mass of the ice melt equal to the decrease of the reading. Now from the question, they already say electronic balance decreases by 0.172 kilogram. So finally, we can say about the balance decreases is how many? 0.172 kilogram. We just copy from the question. Okay, second one, they want you to calculate the latent heat fusion of the ice. So from here, we need to apply the formula. Okay, PT equal ml. Now the question we need to find is L. So we create the equation. PT, P is 480, T is 120. Okay, so from here, 0.172 is the mass. Okay, you need to find is a fusion, latent heat of the fusion. So from here, we just take 0.172, put at the hours, divided. Final answer, there's a 3.35 times 10 power of 5 joule per kilograms. So that one is your latent heat of fusion of the ice. Okay, next see another example. Amount of the heat supplied by the water heater. Okay, change the 0.75 kg of the water at 30. Then to the steam 100. So for this one situation we assume no heat loss. So all the heat provided, the straightforward convert. Okay, so from here, the situation, we need to see two important things. First, the temperature changes. Number two, the phase also changes. So for this one situation, can you see they provide the info, heat specific capacity, and also the latent heat of vaporization. So that means this concept, we need to using these two of the specific and latent. Now we go and write the equation first. Okay, when starting, there's a 0.75 kilogram water at the 30 degrees Celsius. Then after that, you need to make it become the steam 100. For this one, same situation, we cannot both together changes. We cannot change the temperature and also change the phase together. We need to either one. We need to separate. So from here, we go and choose water 30 degrees Celsius. Either you want to change become steam 30 degrees Celsius, or you want to change become the water that's 100 degrees Celsius. Now we're going to see which one is more logic. Normally the more logic is you change become the water still 100 degrees Celsius. If you say you change become the steam 30 degrees Celsius, we cannot say steam is a 30, is it? Normally become the steam already is 100 degrees Celsius. So from here we convert the temperature first. So that means you find it, water, go another water, but now it's 30, go 100. So for this one situation, we need to using is a specific heat capacity. Okay, now we continue. We want to convert become steam. So now already is 100 degrees Celsius. So I can convert straightforward also 100 degrees Celsius, but now the phrase is a steam. So now this one situation, I just change the phrase. I never changes the temperature. So we're using latent heat. Okay, now we can combine together to find the amount of the heat. So amount of the heat is a Q1 plus Q2. So we apply the formula, all the info from the question we just put in. So we find it as a 1.92 times 10 power of 6 unit of the heat, that's a joule. Okay, then we go to another question. They show you the figure, there's an electric steamer. Now you need to explain how come the food can be heat. Okay, now you're going to see. First one, we're using the water, stay at the bottom. So this one is a water has a large specific latent heat of vaporization. So from here, this property that enable the steam to be used for cooking by the method of steaming. So when the steam just condenses, steam condenses on the food, what happened? Latent heat is released directly onto the food. Finally, the food to be cooked faster rate. So this one is why we're using the water to steam the food. Okay, second one, we got another question. There's the amount of the heat released when 0.8 kilograms of the water at 25 degrees Celsius. Now this one they need to cool down. They cool down, become the ice, -6. So state the assumption you make in your calculation. So what assumption we make it? Assumption is no heat loss. That means all the heat from the heater that we use to melt the water become the ice. Okay, let's see the info. They give you capacity for the water. They give you the capacity for the ice and give you the fusion of the ice. So we still write the equation first. Okay, when starting, there's a 0.8 water in 25 degrees Celsius. Now I need to convert to the either ice, either temperature change. So you from here, if you change become the ice, then your temperature must keep 25, is it? So from here, we don't have any situation, the ice still 25 degrees Celsius. So we need to change. We go to change the temperature first. From the water, go water. Okay, but the temperature becomes 0. Okay, water 0 degrees Celsius, we still can be accepted. So from here, we find it there's a specific heat capacity. Okay, after become water 0 degrees Celsius, okay, now I can convert 0 degrees Celsius become the ice. So this one situation is a latent heat of fusion. Okay, last, the ice become ice ready. Now you need to drop the temperature, become -6. So this one is a specific heat capacity again. So now we got 3 of the heat. We need to combine to find the amount of the heat. Okay, so from here I get it. All the number you just put in. Then after that we go to multiply. After multiply plus together, we get it the answer for the amount of heat released. There's a 3.608 times 10 power of 3 joule. Okay, so this type of the question we need to write the equation first before we want to add together. Okay, so our lesson just until here only. Thank you for your watching.